So this is a video in the Engineering Science series, and this particular video we're going to be looking at the binomial series, and binomial comes from the format where we have a plus b raised to the power n binomial, because there are two terms in here. So if we just do a very quick example of that, I've got a plus b raised to the power 2, and we should already know that that is a plus b, undo that, a plus b times a plus b, and not a squared plus b squared. And when we do the expansion of that, so in other words, I'm going to do a times b, a times a times b times a, and b times b, and that comes out as a squared, that's my a times a, plus ab plus, well, b times a is the same as a times b, so I've got another ab plus b squared. Gather up the terms and I have a squared plus, how many ab's have I got? I've got 2 of them, so I've got 2 ab's and I've got 1 b squared. And I think it's important at this point to note that that 2 here, which is known as the coefficient of AB, the word coefficient really, when you're looking at these terms, is you're saying to yourself, when I do this expansion here, so I'll underline that, when I do this expansion here, how many ABs, how many terms with A times B do I have? And I have 2 of them, therefore that coefficient is 2. So let's try another one. Let's do it in a different colour, just for fun. I'm going to come right over to the side, so I'm going to need a little bit more space, and I'm going to say, let's do a plus b cubed. Now I'm going to write this out in full, but you should already know this is going to be a plus b times a plus b times a plus b. I will do this underneath, and that is going to be a cubed plus a squared b plus a squared b plus a squared b plus ab squared plus ab squared plus ab squared plus b cubed. Now, if you don't believe what I've just written down there, stop the video and go back through and go a times a times a cubed, a times b, a times b times a, and so on, and you'll find that you get that line there. I've written it out with the a, or the a's first and the b's second, and obviously when you start doing the b times a, if you would write it down in its purest form, then it would be in a slightly different order, but this is what it amounts to. So I've got 1a cubed plus, look here, I've got 1, 2, 3, so 3 times a squared b occurs in this equation, in this expansion, 1, 2, and 3. And it's 1, 2, 3 times that b squared occurs. So I've got ab 3 times, so I'll convert 3 ab squared plus and there's this single at the end here, b cubed. B cubed. So I've got an a cubed, 3a squared b, 3ab squared, and a b cubed. Now there's a pattern forming here, so I've got 1, 3, 3, 1. If I go up here, I've got 1, 2, 1, and actually what that pattern is Pascal's triangle. So let's write that down. Pascal's triangle. And if I was to draw Pascal's triangle over here, I'd 1, and then I'd have 1, 1, then I would have 1, 2, 1. You can see a pattern here. 1 plus 2 is 3, 2 plus 1 is 3, 1. Look where it is, 1, 3, 3, 1. And that could go on to the fourth and the fifth powers. And actually when you get up to sort of 8, 9, 10 and even more powers, this becomes a little unwieldy to work out what the expansion is. There's also a pattern, I don't know if you've noticed that, in the powers. So if I look here, I've got 3, a to the 3, a to the 2, a to the 1, a to the 0, b to the 0, b to the 1, b to the 2, b to the 3. So actually if I was going to do any expansion, the first thing I could do is to use that pattern to write out my expansion. So let's try that, leaving aside the fact that these coefficients, we'd have to find some way of doing these coefficients, but certainly if I was going to do an expansion of any of the binomial series, then I could use that pattern. So let's use that pattern in a plus b to the fourth. Simple, really. So using the expansion that I just said, and I'm going to do it just slightly underneath because Pascal's triangle is going to get in the way if I don't. So I know I'm going to have an a to the 4. Alright, let's write that down. A to the 4. And there's only going to be 1. All of the Pascal's triangles always start and end with a 1. So I'm now going to have a to the 4. And all I need to do is to write down the other expansions of that a. So there's a to the 4, a to the 3, a to the 2, a to the 1, and then a to the 0. I'm going to put a to the 0 here, just for completeness, because that'll cancel out because it just equals 1. So yeah, you remember that anything raised to the 0 is going to equal 1. Anything raised to the 1 is going to be equal to itself. So then the pattern for the b's, I've got a b to the 0, b to the 1, b to the 2, b to the 3, and b to the 4. So one of the patterns that should emerge, and a quick check for you, is if the power series, so let me just pick a different colour here, let's pick green. So the power in this series is 4. 4 plus 0 is 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. And 0 plus 4 is 4. So check. I've got that series has been expanded out correctly. What I've got missing now is the coefficients. Okay, so I'm going to write in here a c for coefficient, a c for coefficient, and a c for coefficient. To complete our sum, let's put a plus, and a plus, and a plus, and a plus, because I know the coefficient of the first term is going to be 1, and know the coefficient of the last term is going to be 1. That leaves us the coefficients here. And the way that we mark this out is we say, we always put the power at the top of the coefficient, so it's the fourth power, that's the fourth power, that's the fourth power, and this is the first term that I have a coefficient other than 1. This is the second term, and this is the third term. Give myself a little bit of space. I haven't got much more space left. So in order to work out the coefficients, there is a little formula, and that formula is that term here. So what colour haven't we used there? Green we haven't used there. So this term here for that coefficient is where we have c to the n, and n is up here. So up here I've got a plus b to the n. In this case I've got a 4. So c to the n, and at the bottom it is whichever term that is, and the term is r. We'll put as r. Where c to the n over that equals n factorial over r factorial times n minus r factorial. Sounds like a lot of factorials there, but I promise you, let's have a quick look at c to the 1, which is what we're looking for over here, and that would be equal to 4 factorial over, well, r is 1, so I've got a 1 factorial. N is 4 minus r, which is 1, so that's 3 factorial. Let's write them in. 4 times 3 times 2 times 1 over, we don't need to do 1 factorial because this is 1, so that is 3 times 2 times 1. Hold on a minute. I can cancel some of these out. In fact, cancel them all out. That's going to equal 4. And so my first coefficient in this expansion is 4. And actually, if you do the sum for them all, and I encourage you to do that, you end up with a 6 in that one, you end up with a 4 in that one, which kind of follows what we would expect the next line on Pascal's triangle to be, because that is 1 there, and that is a 1 there, so the expansion of Pascal's triangle, the next line would be 1, 4, 6, 4, 1. Hold on a minute, 1. So I've got 1 there. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And a 1 on the end. 1, 4, 6, 4, 1. So using this formula here and the patterns that we have learnt, we can do the full expansion of any binomial series where we've got a plus b raised to the power n, and this works as long as n is an integer. So that ends the first in what I think is going to be 2 videos about the binomial series, because I think on the next video we'll do another example just to show that we have done it correctly. So we'll see you in the next video.